This is Garis MPC, Math, Physics, Computing, 130 plus Masters and PhD level courses in pure math and mathematical physics. This is course number 4, so MPC 4, on linear algebra, a junior and senior level course. This is lecture or chapter 2. And session number, or session F. Now, the previous session we were about to start solving a linear system, and its nature, it was non-homogeneous. So that means that at least one of the b's, the constants of the equation, was non-zero. Now I've written out the system here. Remember, just the system is just a set of linear equations. So 3 equations. Now I'm putting one equation per line. So one equation, one line, one equation. So so I'm just labeling this line or equation L, L for line. So L1, L2, L3, so for the 3 equations. Now, the strategy, with Gaussian elimination, the strategy is to rewrite these 2 equations below the top one. You just keep the top one as it is. So long as your coefficient here is non-zero. If it is 0, then find some other equation where the coefficient is not 0 and just swap them. So you want to start with your first line. This coefficient here is to be non-zero. Okay? Right, so now we will now replace the second and third equations, or lines, with equations that are shorter, where the coefficient of the x in the new line 2 will be 0. So in other words, that x is just gone. This here is gone. And so you're just left with some coefficient y. So in a sense, the x has been eliminated. And similarly for the third equation. So we want to replace line 2 by some shorter equation, some shorter line. How to do that? Well, the trick is you have a look at this coefficient and you have a look at this coefficient, and then you do the following trick. Now we want to shorten this equation. So we want the coefficient here to be 0, so that we eliminate this x term. So we can, if we multiply this whole equation by 2, we'll get 6x here. And if we multiply this whole equation by -3, you get a -6 here. And then we just add. So that's what's going on here. So so if you multiply line 1, in other words equation 1, that's this, by -3 all the way through, you'll get this. Here it is. Okay. So this line here is equation 1 all multiplied through by -3. It gives you that. And similarly, you multiply all of equation 2 by 2. So here it is here, 2 times line 2, equation 2, same thing. You'll get this, and you've got a 6x and a -6x. So now add 3 times line 1 plus 2 times line 2. So 3 times that, sorry, -3 times that plus 2 times that. Your 6's will cancel, so the x term is dropped out, and your So this equals this. There's your new equation. That will become your new line 2. So here, if you look at this is sort of shorthand. What it's saying is this arrow, I guess you can read that as replace line whatever's here. So replace line 2 by whatever's on the right hand side. Okay. So and similarly for we want to eliminate this coefficient here in line 3. So again we'll use equation 1 and equation 3. So if I multiply that by -4 and I multiply that by 2, so I'll get 8x here and I'll get -8x there, and then add L1 where is it? Here, yeah. So by multiplying line 1 by -2, so I'll get -4 here, and add the result to just L3, so I've got a 4 here. So the coefficients of that sum of x, 0. So you've eliminated the x. So so here's -2l. So you -2l here. Here it is here. So just multiply line 1 by -2, and you get this. And then you add line 3. So here's line 3 just written out again. Now, what's on the right hand side will be this. So you just you add up the two equations, and you'll get 3 equals 1, right? So this line here, that becomes your new line 3. So you replace the old line 3, so you replace this one by this one. And so now you've got an equivalent system. Remember, a system's just a set of linear equations. So you now got an equivalent. Now, what do you mean by equivalent? A bit of a revision. If you have two systems, your original system and an equivalent system, so a system equivalent to the first one, all that means is that the equivalent system has the same solution, general solution, as the original one, right? That's what equivalence means. Right. Now you can see interestingly here, not only has the x term disappeared, but the y term has also disappeared. That can happen sometimes, or even more. But you can see now that the second and third lines or equations are now shorter, because we've got rid of at least one of the variables. In fact, in this case, for both of them, we got rid of 2. Right? Okay, now a few remarks. You might end up getting something like this. You have the coefficients of your equation on the left hand side. If they're all 0, but you've got the constant of your equation b on the right hand side, if that's non-zero, you've got a problem, because the left hand side is obviously 0, and you're equating that, you're equal to something on the right hand side that's not 0. Well, that's a contradiction. You can't have that. So if this situation arises, then that equation is said to be inconsistent. And if you have an inconsistent equation in your system, in other words in your set of equations, then the system is said to be inconsistent, and so there's no solution, right? So inconsistent and has no solution. There's no solution to the system, to the set of equations. Now another possibility you may end up getting, the left-hand side is 0, so all these coefficients end up being 0. So you've got 0 on the left-hand side and on the right-hand side. So when that happens, so when you end up with 0 equals 0, just throw out that equation. So you just eliminate it from the system, because it contributes no information about the unknowns. Because if you have all zeros here, then these x's can be anything, and that's not very interesting. So when you end up with an equation that's of the form 0 equals 0, throw it out. It's not useful. Okay? Stop there.